welcome to week 3. And of course, the theme is, as always, this is all summer classes here and all summer classes everywhere are always an accelerated speed through what would normally be something that you would have a lot more time to digest and work your way through. So, full understanding and full sympathy for the pace of these courses. Um, but we are definitely moving on and moving on to area in which, again, we continue this theme of sort of building up from sort of simpler estimations and understandings of how an individual atom might work and all the atom's individual subcomponents, protons, neutrons, and electrons. But now, quite importantly, moving on to something which most people care more about, which is going to be how do they behave? How do we predict this aspect of bonding? Of why do we form certain molecules? Why do those molecules have these shapes and the properties that they do? And it's definitely a much longer topic than we would have within essentially 1 week to cover this particular subject. It's one that, as you take more chemistry, you'll come back to again and again. This is really the big crux and really the big sort of punchline of most of chemistry is how do we predict these shapes, structures, and properties of molecules. So today we're going to get sort of a very uh, much a first look at it, but it's one thing that we'll come back to again within this course, and you'll come back to again as you do the rest of your biology courses, if you take material science, if you take other advanced topics in science. This is definitely something that many scientists spend most of their time worrying about. Again, to review sort of our thesis and our aim here is to try to improve upon what sort of ancient alchemists did of old and try to be more predictive, to be better able to predict before we run the experiment what should happen. In some cases, we want to sort of make sure that we save our time and effort and materials, but in many cases, many of us will become concerned with being able to predict whether reactions occur or not for reasons of safety. We don't want something to blow up when we didn't expect it to, and vice versa. And so, really, we're trying to establish rules. And today's rule, and really the most important rule, is how do I tell what happens when I push two atoms together? Will they interact favorably? Will they repel each other? How can I predict this? What rules do I need to have in mind? As a bit of review, again, a lot of our sort of early on lift is just dealing with the language of chemistry and trying to make sure we're all speaking at least different dialects of the same language of chemistry. And we are very much working towards describing a chemical in mainly 3 ways. Full recognition that this is very complex and something that not even chemists all agree upon. Again, there is sort of this weird thing like any language, different chemists will speak sort of different dialects of chemistry and refer to things a little differently. Hopefully, all chemistry refer to things by the same chemical formula. This again is our list, sort of our receipt or itemized list of all the elements within a compound and their ratio. Where we may differ, we may call things different elements. We may call things different molecules or different compounds. We may disagree on the name or have several names to describe the same compound, or indeed the same name to describe different compounds quite confusingly. But all of it should anchor down to the same 3D molecule, the same representation at the atomic level. That actually is what dictates a lot of the properties. How are these different elements in different ratios arranged in three-dimensional real space? We spent some time last week dealing with the first and the second sort of way we describe a chemical. This last one is really where we're building to this week. As we sort of begin to write and denote, indeed you've had some practice with this already, different versions of different elements. We of course use our elemental symbol, which is this 1 or 2 letter abbreviation. Make sure that your handwriting or interpretation is distinct enough to tell between uppercase and lowercase letters since they mean different things in chemistry. And something we often see is of course both the pure element, magnesium for example, but magnesium, after having undergone some sort of chemical change, which we'll talk about today, in this case, magnesium commonly loses 2 of its electrons to gain a net positive charge. We call these things that are net positive a cation, so a magnesium 2 plus cation, to distinguish it from an ion which would have gained electrons. Again, we'll work today to predict why and when this happens. Negative charge ions we would call anions. This chemical formula, which you'll commonly use throughout this level of chemistry, really tries to, again, tell you everything found within a compound. If it's not within the chemical formula, it's not there in great abundance. Again, there's always impurities. But as far as we're concerned, the chemical formula is the authoritative list of everything found within that material. Now, we want to specify the ratio of each element. We may call this ratio a stoichiometry. But again, it just tells us how many of each element is found within this compound. Some subtlety comes if we're describing what we would think of as a molecule, which is going to be a discrete finite cluster of different elements. We would call this in some cases a molecular formula, and this molecular formula itemizes the total number of each element found within this one cluster of this particular compound. So water, with a chemical formula of H2O, means 2 hydrogens to 1 oxygen. And every molecule, every little cluster of H2O is going to have the exact same ratio, but of course the exact same number. If you were to have H4O2, you'd have a same ratio, but of course a different molecule, very, very dramatically different properties. We sometimes write this molecular formula in an expanded version, particularly because quite often with carbon, hydrogen, and oxygen, there's many compounds that have the same chemical formula, the same molecular formula, same list of elements, but might be arranged in different manners. And often we'll write these molecules in a structural formula, which tries to sort of space out the different subclusters within this molecule to tell us how they're bonded together and give us some idea about the more detailed shape of this particular molecule. In this case, ethanol, sort of the alcohol that we consume, hopefully not on too regular of a basis. These molecular formulas do differ from an empirical formula, and without knowing more about chemistry, just seeing these different formulas is very hard to tell which one is the other. We'll build towards those rules to be able to identify a molecular versus empirical formula. But at least for now, our definition of an empirical formula typically implies a ratio of each element, not an absolute fixed number, but a ratio. In these cases, something like sodium chloride, which is table salt, has an empirical formula of NaCl. This does not mean typically that you have one Na bonded to one Cl floating around as a 2-atom molecule. We usually see things with empirical formulas are composed of ions, a positively charged sodium plus, a negatively charged chlorine minus or chloride. These positive and negative charges in this ionic compound composed of ions, we typically see as large crystals, alternating units of positive and negative charges, for which this formula quite rightly represents that we have a 1-to-1 ratio of Na plus and Cl minus, but sort of the actual cluster of atoms that we encounter in nature is probably a trillion plus atoms of sodium plus and an equal number of trillion plus atoms of chloride minus, all bound together in this crystal. Importantly, this empirical formula most often balances out to a neutral compound. So however many positive charges we have has an equal number of negative charges. One thing that did pop up as I started preparing for the coming lectures, one thing you might also see is an empirical formula of a hydrate. Now this is a slight variation. Many compounds you're likely to encounter exist as what we call a hydrate. You may think of this as sort of a solid mixture of 2 different molecules, some sort of compound and water. Unlike any other solution or mixture of stuff dissolved in water you'll encounter out in the real world, seawater being a mixture of sodium chloride and water, these hydrates are a stoichiometric mixture and often appear as a solid crystal. So we may encounter something like magnesium sulfate, magnesium being one of our pure elements, and SO4 representing again one of these polyatomic anions we call by a special name sulfate. Now magnesium sulfate has a chemical formula, an empirical formula in this case, and it's a large crystal composed of ions. And we'll represent that this crystal of magnesium sulfate, sometimes also referred to as magnesium sulfate anhydrous, just contains 1 magnesium to 1 sulfur to 4 oxygen. We could also calculate a molar mass. That 1 mole's worth of MgSO4 weighs a certain amount, 120 grams or so in this case. If you were to find just a rock, random rock, that contains magnesium, sulfur, and oxygen, you may find that within this crystal of this ionic compound, there's a little bit of water trapped in there. And not a random amount of water, but a stoichiometric or an exact ratio. For every magnesium, sulfur, and 4 oxygen found within a crystal of magnesium sulfate monohydrate, you would find 1 water molecule mixed in there. This water molecule is not bonded in the same way that we think the magnesium, sulfur, and oxygen are bonded in there, but they really are just mixed in there in sort of, again, a solid mixture. Things like alloys sort of also fall into the realm of solid mixtures of different compounds commingled together, not bonded in the same way that we would think a compound is, but in this case, a very specific ratio of 1 Mg to 1 S to 4 oxygen, all of that in the ratio to 1 molecule of water. You'll notice that because now every mole's worth of magnesium sulfate also implies we have 1 mole's worth of H2O, we calculate that this molar mass is slightly heavier, plus the mass of this 1 water molecule. We point this out because quite often the thing that we encounter in the real world, if you were to find magnesium sulfate sitting on a shelf in a laboratory or an ore out in nature, you are probably most likely to find magnesium sulfate heptahydrate, indicating that for every magnesium sulfate, there are 7 water molecules exactly associated with this MgS and 4 oxygens. This little dot between the MgSO4 and the 7H2O highlights the idea that this is not quite one compound in the way that MgSO4 forms, but again, a mixture between water and something else. The reason we point this out is that the calculation of the molar mass, how many moles of magnesium sulfate per mass you might measure, changes because now there's water sort of carried along with the mix. For these ionic compounds, the issue of naming is probably as simple as chemical naming does get. Usually we sort of get just the cation name, often sort of a metallic species, and the modified name of the anion. So previously we saw sodium and chlorine bonded together in an ionic compound. And so we would refer to that as sodium chloride, taking the name of the metal and adding this IDE suffix to chlorine. We will similarly name barium and chlorine as barium chloride, potassium fluoride, potassium bromide, so on and so forth. The one example, the one exception to sort of the simplicity of the naming is when we deal with metals that come from our D block, this row and set of elements found sort of in the middle of our periodic table. We don't typically deal with that too much in this general chemistry course. That is something for the topic of inorganic chemistry in particular. But we still, of course, deal with iron and things from time to time. Again, things found in our D block. For reasons of their atomic orbitals, which again will not get too deeply into this course, things like iron can commonly exist quite with even abundance as either a +3 cation or a +2 cation, sometimes a +4. And so quite often we need to specify what type of iron we have present, whether it's a 3+ cation, represented by this Roman numeral 3, or by sort of the more archaic name ferric chloride, to help distinguish it from a +2 cation version of iron, ferrous chloride. Still, we generally follow this convention, and most ionic compound names are interpretable. What the name says what's in the tin, tells you what elements there are bonded together. You may also see ionic compounds, things with empirical formulas that are polyatomic ions. These again are a combination of a cation and an anion, but these ions might be themselves molecules. In this case, a crystal of baking soda is a combination between a sodium cation and the bicarbonate anion, HCO, HC and 3 oxygens, all bonded together like a molecule, but carrying a net negative charge. These all sort of pack together like our sodium chloride crystal does in ratios rather opposed to fixed numbers, but still sort of combines both a molecule and an ionic compound together. The trick with this is that these polyatomic ions, unlike our periodic table, which has a very finite set of names, have many names that sort of you just have to learn by example and as you continue to go through them. This is not a list that I expect you to memorize, but one that you will begin to become more familiar with as you spend more time with these molecules and as we revisit these chemicals again and again. But to point out, different names imply different chemical formulas, which imply different properties. So just be careful and mindful of naming and chemical formulas as we deal with these polyatomic ions. Our look at names for our molecules, things are represented by a molecular formula, can be systematic. Sometimes we will use Greek prefixes to tell how many oxygens there are bonded to a carbon to distinguish toxic poisonous carbon monoxide versus what we breathe out and respire, carbon dioxide. But quite often we sort of use much more historical, sort of antiquated names that you just kind of have to know what they are. Again, one reason why I really have an open resource policy for this course to help simulate really how you will spend the rest of your lives interacting with chemistry is a lot of these things are best looked up to verify and double check that everyone's talking about the same molecule, the same substance. Sometimes we may refer to it by the chemical abstract service number, the CAS number, which every string of numbers, sort of like a serial barcode, refers to a specific molecule with a specific chemical formula and a specific structure. But for the sake of being very, very accurate as well as fast, I do always encourage you to double check yourself using your favorite resource. If you don't have one readily available, I'm happy to make some recommendations. These days, Wikipedia is pretty accurate and pretty reliable for a lot of chemical information. So if that's what you use, that's a perfect way to be both fast as well as accurate in terms of what compound you're dealing with. Last week, we also talked more about the idea of a mole, this numeral grouping that allowed us to do a lot of work in laboratory, trying to relate the ratio of counting atoms, counting each element within a compound, like this magnesium compound we made, but relate to something we can more easily measure, grams instead of atomic mass units. Now, from our discussion last week, we spent a lot of time talking about the inner structure of our atom, this combination of protons, neutrons, and electrons. And electrons in particular were the weirdest part of it. Protons, sort of a nice spherical, hard little subatomic particle, positive charge. Neutrons, not a lot of chemical effect at this level of chemistry, no net positive or negative charge. And the electron, we are welcome to think of in terms of a very, very tiny, effectively massless little negatively charged particle. But as I hinted a little bit, electrons are the weird bit where, for the longest time, really not until the last 60 years or so within some people's lifetimes, have we really understood very well that this electron does act like a particle. We can count it like a particle. We can count negative charges like we count positive charges of a proton. But also exhibits some weird thing that we would group under this idea of a wave-particle duality. The electrons do behave like particles, but also like a wave, like a light or a wave in the ocean. And the way that we sort of figured this out is by trying to measure things through experiment. Again, we do experiments in this lab, one to verify the laws and rules that we've been running with are true and reasonable. And scientists and physicists from about the 30s onward were really concerned with trying to run experiments to test this idea that an electron is just like a little planet circling a larger sun, and we can predict the behavior of an atom like we predict the behavior of a solar system. And so if you had an electron that behaved like a particle, or really anything that behaved like a particle, if you had two barriers, one sort of a screen that collected where your particle landed, a grating or a gate, here featuring two little slits spaced very, very closely apart that allowed these particles to flow through specific apertures through a specific thing. you would expect as particles that they would flow directly through those slits and land in two little spots on your target screen. You can think of this if you were to shoot a paintball gun through two little holes in a wall. You would see two little holes on the opposing side, maybe your opponent, since all of these sort of move through under very sort of normal Newtonian mechanics. They thought they would test this idea out with something that they thought was likely a particle, and they tested out with a photon, with sort of a single little particle of light. And what they found is that instead of two nice little dots, when they fired light through this tiny little pair of slits, they saw not two little bright spots, but they saw this range of spots spaced out at very interesting and very regular intervals. These spots varied in intensity, but they all featured sort of a very interesting repeating diffraction pattern. And so they had to revise their understanding of a photon, that rather than being like a specific particle of light, which it does behave a little bit like, it really behaves like a wave. Like if you were to drop a pebble in a very still lake, you would see waves propagate out from that individual stone dropped in the lake. By analogy, as a wave passes through these little slits, unlike a particle, which will sort of carry on its momentum in a straight line, the wave sort of reinitiates this ripple effect from each slit. These ripples are represented by sort of troughs and peaks, sort of high and low points of this wave, or sort of intense and diffuse areas of light. These waves interact with each other very much like you would see ripples on a pond. And this interaction, where the wave peaks meet up, or the wave troughs meet up, or in periods in which the phases are opposite, you'll see places where they add up together and places where they cancel each other out. This is how they explain, and the reason why they saw this sort of repeating pattern of light is that they saw this interaction between the various troughs and peaks of these waves. And so they thought, great, sort of we understand how waves work. We've lived on boats. We know how boats work. We can predict and model a lot of this physics for something like light, which we now refer to as having a wavelength. They repeat this experiment with electrons, thinking, great, electrons are particles. We should see this pattern. Two slits, two spots where the electrons hit our screen. But when they ran this experiment, they saw that even though we only had two slits, where these electrons landed on their photographic paper, recording their position, they saw these electrons not only spread out, but they saw that they exhibited the same sort of repeating diffraction pattern that the light would. They found that if they slowed it down and they sent a single electron through the slit at a time, they watched that electron and they made sure they saw when the electron left and when the electron landed, that they would see this pattern. But if they let all the electrons flow at once, sort of as they would through a very, very fast stream, they saw this diffraction pattern. It posed to them a very, very confusing thing of depending on whether you watch the electron or not, depending on whether you fire them one at a time or let them all flow together, you would see them behave either like a particle, making only two spots, or as a wave. And indeed, for the last 70 years or so of physics and chemistry have been trying to reconcile this. We've always thought of electrons as particles, and in many ways, much of our chemistry still deals with thinking of electrons as tiny little planets circling around a nucleus. But more accurate predictions and a lot of the weirder things we see in chemistry, and perhaps a more predictive set of rules, comes from considering them both as particles, but also as this wave-like behavior. Last week, we talked a lot about electrons in terms of their particle-like behavior. We thought the proton is a particle, the neutron is a particle existing as a cluster, sort of the center of this solar system, found within this nucleus. And they have a mass, they have a charge, and the electrons are sort of this weird intermediate between a particle and an electron, that as the screen comes back, we'll be able to continue on. And as we deal with sort of the technical difficulties of this particular finicky USB-C type connection, we spent a great deal of time thinking about this analogy of an electron and its atom as like a city and its residents. In this analogy of a city with a set of residents, obviously we can think very much of people as particles. We know where people are. People don't really exist as waves unless you're a very particular type of person. And so we were very right in sort of setting up this neighborhood map of an atom and thinking of these individual electrons as living within certain rooms of certain houses, which we sort of called orbitals, subshells, and shells. This was a very reasonable, and again, still a true way for us to think about how electrons behave as existing and living a certain distance from our nucleus in a certain shaped house. This particle idea, this particle definition of electron, helps us again to sort of see the differences between each individual element as having different number of electrons, different number of residents of the city that live in increasingly further and further distances from the center of our atom. We refer to all of their different addresses by these quantum numbers, typically a number, 1, 2, 3, 4, 5, to represent sort of the largest gross differences between where they live, and the type of house as these orbital shapes, subshells and orbitals, S, P, D, F, so on and so forth. Like any sort of person, they fill out from the closest, lowest energy orbitals on out. They can only fit 2 electrons per room or 2 electrons per orbital. And if they have the option, they'll sort of split themselves up evenly amongst the different rooms of this house before they're forced to double up. And this interpretation, which is very, again, thinking of these as particles that live at a certain location, is still how our periodic table was devised and is arranged, very much before we sort of start thinking of electrons as waves. Based off of this, we can group this periodic table between something like an S block, which has its highest energy, last filled electrons, most reactive electrons in an S-type orbital, versus a P block or D block or an F block. We do so again because we have observed empirically, we observed experimentally, that things found in the same column exhibit very similar electronic structures and very similar reactivity, very similar types of chemical reactions. Similar things in the same row have some common properties between them that allows us to make predictions and interpret the rules of how these individual elements behave. A lot of the best use of this periodic table is interpreting it like a map, sort of like a game of Battleship in which the row and the column, the period as a row, the column as a group, tells us something about the structure of this atom and, of course, its properties. We looked at the example of magnesium, found here in our second group, called the alkaline earths, and our third row or third period. And based off its position, we know that its 12 electrons are divided first up by filling up the entire 1 shell, so the 1s orbital of the 1 shell. Then an entirely filled 2 shell, 2 electrons in the 2s orbital, 6 electrons in the 2p orbital, and the last 2 electrons, the 11th and 12th, have to live furthest away from magnesium's nucleus in the 3s orbital. As one reason why this left 2 columns are called our S block, because everything in this column has electrons filled up to some sort of S orbital, giving similar reactivity, similar properties. We use this most commonly because we as chemists really don't want to account for every single electron. We really only care about these most reactive valence electrons, the one found in this highest numbered shell. And we can draw an analogy for everything found in the same column. So nitrogen found here in the pnictogen or pnictide group has a valence electron configuration of 2 electrons in an s orbital, 3 electrons in a p orbital. One below it, same group, same column, phosphorus has the same pattern of filling, but now to the third shell, but still 2 electrons in an s orbital, 3 electrons in the p orbital. Arsenic follows the same pattern, as does antimony, and as does bismuth. So we use this because the position allows us a shortcut to predict something about their reactivity. If we know a little bit about how nitrogen behaves chemically, how it reacts, how it bonds, how it undergoes reactions, it tells us a little bit about how we expect phosphorus to behave, as well as arsenic, as well as antimony and as bismuth. Chemistry is complex, so we typically stick our discussions mostly to these smaller atoms, nitrogen and phosphorus. As you get to these larger atoms, which you see now incorporate D and F orbitals, some of the rules become a little harder to track, a little more complex. But most of what we'll do deals with sort of these first three periods, these first three rows of the periodic table, because it's easier to create simpler rules to predict how they behave. We have some periodic trends based off this similarity. Things found in the same row all feature filling up to the same numbered shell, but increasingly more protons as you go from left to right. We build this intuition that as we add more protons, more positive charges, it pulls a stronger electrostatic force in each of those electrons, each of those orbitals. And so going from the 6 protons of carbon to the 7 protons of nitrogen and the 8 protons of oxygen, it should pull those same 2s and 2p orbitals closer to the nucleus, stronger electrostatic pull. And we represent that by showing them lower in energy, sort of more stabilized as they're closer to the center of this atom. We see that makes, in general, smaller atoms as those electrons are pulled closer and tighter to this nucleus, and requires more energy to remove these electrons to sort of pull them away from our nucleus as they become lower and lower and more stable. Eventually, this difference between the same 2s, 2p orbital between different atoms gives rise to a lot of different properties of why carbon behaves differently than oxygen. And if those two were to interact with each other, as we'll see today, how we can predict the nature of their interaction. We can also pick some properties as they go down the group. Again, they fill to the same pattern. Nitrogen, phosphorus, and arsenic all have the same type of valence electrons, 2 in the s, 3 in the p, but fill to higher and higher shells, further and further away from our nucleus, higher and higher energies. Now, most of our discussion of chemistry from here on out, again, deals with these electrons that are furthest away from the nucleus, the ones that are held on most weakly by the atom, the ones that are furthest away, highest in energy. And we should build this analogy, and it does carry through, that if you were a person living on the outskirts of your metropolitan area, let's say you live on the outskirts of the greater Boston area, it's quite a hassle to go into downtown Boston. You have to park, you have to find accommodations, whatever it might be. And you're more likely to leave the Boston area if you're not sort of in a good location, very, very close to all the central amenities. How and when electrons decide to leave their home atom and move to a different atom, hopefully to be closer to some other city, to some other dense metropolitan area, is really a comparison of how close can they get to the center of an atom. Doesn't matter if it's their original one or a new one, which we think again as sort of this electrostatic attraction. How strong can this pull be? How low in energy can these electrons get and stabilize? But our understanding of how these electrons move, when they move and decide to sort of jump ship, as it were, really requires us to think about how do electrons behave when they move. And as we saw in the double slit experiment, when electrons are moving and interacting with other electrons, it's important that we consider how they behave like waves, since they do interact not with just what they collide into, but what sort of they feel by wave proximity. A little thing on waves. So there's no requirement to have taken physics very recently for this particular course, but potentially you have in a previous class, a physics class, sort of talked about waves and built a little bit of intuition about how we think about waves. A common way that we sort of see waves is as sound waves. They might be sort of a vibrating string of a guitar. They might be sort of air vibrating and moving down the tube of a trumpet or a tuba, so on and so forth. And there's a couple of things about the nature of these waves that we observe across all waves, whether it's a wave in an ocean or a plucked string or a bit of air blown into a tube. Every time we see a wave that particularly is moving between two different surfaces, in this case, we can imagine this as a sound wave going through the tube of a trumpet, for example. We see that there is a positive amplitude and a negative amplitude as it vibrates up and down, high density, low density, whatever you might want to call it. And each of these waves needs to sort of terminate in what we think of as a node. A node is going to be any position on our wave in which we see zero displacement. So as our wave vibrates up and down, or for example, our guitar string vibrates up and down, there's always going to be a fixed point, maybe between a fret and the soundboard or other fixed points, in which our guitar string isn't moving, in which our sound waves aren't compressing or decompressing. These notes simply just represent where there isn't vibration, where there isn't stuff going on. If you've ever been a trumpet player, or you've had the misfortune of living with someone who's played a brass instrument, you would know that for all the notes that a trumpet can play, that there's only 3 keys, which really isn't enough to give you the 80s, not 80 something, maybe 30 something notes that a trumpet can play. A lot of the way that most musical instruments works is that if you have a fixed length of, let's say, a trumpet, you can blow air through that trumpet, you can pluck the guitar string, and it'll vibrate up and down with sort of one peak, one trough, vibrate up and down. If you pluck that string a little harder, you blew a little stronger into that trumpet, you would hear a note that is 1 octave above that original note. And this corresponds to having a wave of the same sort of fixed distance, but now featuring a node in between. And now 2 regions, one that goes up while the other goes down. They oscillate and vibrate each other. As you continue to blow harder and harder, you would increasingly hit higher harmonics, higher notes, higher energy, higher frequencies that begin to feature more regions of positive and negative amplitude, which we generally characterize and count by having an increasing number of notes. We see sort of that the lowest energy way to vibrate the string has no node, essentially. As we sort of pluck the string higher, more energy put into that string or blown down that tube, we have 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes, so on and so forth. And in general, we can relate the energy of a wave, the energy of a particular vibration, to the number of nodes found within that shape. Electrons, to the extent that they're like waves, exhibit the very, very same idea that as electrons increase in energy, the wave nature of an electron means that we find that they increasingly have a larger and larger number of nodes, giving different shapes, just as the way that our guitar string has different shapes. As we pluck it harder, impart more energy to that vibration. Now, just as our vibrating string, our node indicates where we have no vibration, where the string isn't moving. We're going to begin to think of these nodes as a representation of where we don't find electrons, where we see sort of positive and negative vibrations or amplitude of our electron as a wave. Every time we see a node, we think that that's where we would predict that there's no electrons, that they've canceled out for the normal reasons that waves do. Now, we start with this idea of vibrations and waves in sort of a one-dimensional string case, because it's very easy to visualize and things that we hopefully have seen a little bit before. But electrons exist in our 3-dimensional world, and the question becomes, what does a 3-dimensional wave look like? How do we begin to interpret that shape, that set of nodes, and again use that to predict something about how they behave? As waves begin to occur in higher and higher dimensions, our nodes begin to also increase in dimension. If you were to move from a one-dimensional wave like a vibrating string to a 2-dimensional wave, instead of a node, which would be a point on the string, a 2-dimensional wave has a node that appears as some sort of geometric shape. Could be a circle, could be a line, but some sort of one-dimensional node for this 2-dimensional wave. If you were to have a metal plate, which is the classic experiment, or a drum head, or a rippling surface of a piece of plastic, you would see that you could vibrate that plastic such that the center would go down as the outer edges went up, and they'll oscillate back and forth as you see. There would be a section on this plate where there would be zero displacement, a node of this vibrating plate where the inner bit's moving, the outer bit's moving, but everything along this circular node is not moving, zero vibration. If you were to slightly sort of change where you sort of struck or wiggled this plate, you could see you could also wiggle it such that maybe the corners deflected down when the middle deflected up, and you would have a slightly different shape. You would have essentially still one node's worth, distinguishing one region that goes up and one region that goes down, but different shapes for essentially the same amount of energy for this vibration. As you shook this plate faster, you struck it harder, you imparted more energy to this vibrating plate, you would see more nodes begin to emerge. Now you would see sort of a central region that go up, while a middle region went down, while an outer region went up. Again, higher nodes or more nodes, higher energy, higher vibrations for this particular two-dimensional wave. What this looks like sort of as a realistic visualization is there's an experiment called a Chladni plate that produces Chladni figures. This is a metal plate attached to an oscillator, basically a speaker, that as you increase the frequency of the noise played through that speaker, the plate will vibrate at a higher and higher frequency, higher and higher in energy. What you can do is if you sprinkle a little bit of sand or chalk onto this plate, you'll see that the plate will vibrate, and you'll create regions where it vibrates up and down, as well as nodes where there's no vibration. Where there is no vibration, the sand will begin to collect, forming these little lines and circles found on this plate, visualizing and showing you where the nodes appear. You'll see that in this particular example, which is something I don't typically do because no one wants to listen to 4,000 hertz worth of sound played for a couple hours. As you increase from low hertz, low frequency, low energy, to higher frequency, higher hertz, higher energy, our patterns become increasingly more complex. We get more nodes, more lines indicating where there isn't vibration, and allows us to visualize a wave in two dimensions. You notice that these patterns are very specific. They're probably hard to predict if you were to just sort of sit down and think about what does 15 nodes look like on a vibrating plate. And so a lot of what we do in this wave thing is we do experiments, we do very complicated calculations, and for our purposes, we take the results of those calculations to say, what does a two-dimensional wave look like? Of course, we're not quite there for electrons. We need to consider how does a vibration look like in three dimensions. And for that, it's a little harder to have a nice visual to accompany it. But instead, we have to think a little more abstractly. When we discussed the electron orbitals from earlier, again, sort of this particularly shaped house that the electron lives in, what it really represents is a vibrating wave of an electron. This vibrating wave of an electron is a three-dimensional shape that also oscillates in positive and negative amplitudes. These vibrating shapes, this sort of orbital three-dimensional wave, like a one or two-dimensional wave, will have nodes. The more nodes we have, the higher energy those electrons are, the higher frequency they're vibrating, you may think of. Those nodes also indicate where we don't find electrons, where there's empty space and we don't have electrons to do chemistry with. We also recognize that because this is a wave, our orbital, our three-dimensional wave, should have regions where it has sort of a positive amplitude and regions where it has a negative amplitude, of which negative and positive peaks and troughs of a wave will cancel out. If you look at the s orbital, which we often represent by a spherical shape, we'll see that at the lowest 1s energy, this orbital is a nice spherical shape with really just one amplitude. You can think of this as sort of our first fundamental harmonic string that just vibrates up and down, only one region going up versus down. As we go to higher energy, now to a 2s orbital, still has the same general shape, same general spherical nature, but we now see that there are two different regions of this wave. Ones that vibrate up while the other vibrates down, different amplitudes, different signs, indicated by a node found here between sort of the outer shell and the inner core. It sort of has an egg white and egg yolk type structure. And again, this node represents where we don't find electrons. We sort of find electron probability, electron density in sort of the outer egg white, as well as the inner egg yolk, but nothing at that interface. There's sort of an absence of electrons right there. And again, as we go to the higher and higher energy, to the 3s, we have more nodes indicating higher energy, higher vibrations of these electrons. As we think about these orbital shapes, they do get more and more complex, just like the Claudine figures have more lines, more circles that give increasingly more fanciful shapes. For our purposes, luckily, the solution to a three-dimensional wave for an electron really focuses on two different sort of parent shapes. Every S-type orbital, 1s, 2s, 1s, 2s, 3s, 4s, all have the same general spherical shape, or the same spherical symmetry. They do have increasing number of nodes, different ratios of positive to negative amplitudes, but they also are the general shape, general symmetry. Our p orbital, which has this sort of dumbbell shape, again, sort of we think of it as sort of the wave with sort of a peak and a trough oscillating in different phases from each other. This p shape does get more complex. We add more nodes as we go from 2p to 3p to 4p. But they again all sort of have this sort of mirror image, or sort of opposite mirror image between a top and a bottom, indicating a positive and a negative amplitude, for example. While it's helpful to recognize that the actual shapes of these orbitals do get more complex, most of our discussion from here on out is going to treat every s orbital as sort of a nice round sphere, and every p orbital as a sort of dumbbell type shape, as it's classically described. An important thing to remember about these waves is that the number of nodes simply indicates the energy of that particular orbital. And we'll notice that for the solution for a wave in 3D, for an electron, there are three different p orbitals, one in which this dumbbell points along the x, y, and z direction. Each of these dumbbells all feature a single node, basically between the two halves of this orbital. And because all of these p orbitals have a single node, we recognize that they are all the same energy. One reason why the px, py, and pz orbitals are all the same energy, as sort of the all sort of the same energy. We may call them degenerate orbitals, having the same energy, mostly because they have the same number of nodes. Now, most of our questions are going to become, we kind of have an idea, an instinct, if we were to put two sort of physical waves next to each other. We may have sort of experience if we were to be in a boat with a friend. If both of us made ripples in a pond, we would see that as those two rippling waves interacted with each other, we would get interference where they add up together and interference where they subtract from each other and sort of negate each other. And different variations depending on how fast you're creating ripples and how fast your friend's creating ripples. And this is sort of the intuition that we'll build for our particular look at these 3D electron waves. Our question becomes not what happens when you and your friend in the boat make ripples, but what happens when an electron in one atom and an electron in another atom begin to interact with each other and merge. How do those waves interact? We're going to go to a simulator, which hopefully the technology side of this holds up. As we move them closer, we see that we have more constructive interference, again, assuming that they're both positive. And there's going to be a finite distance, in this case for atoms, of which they can get to. But quite often we'll see if we move them close enough, we'll have a buildup of wave, buildup of electrons here between our two centers, between our two atoms, potentially representing a strong interaction between the two. Electrons found within atoms, acting as waves, have very much the same intuition of how they interact with the electrons of a different atom. Here we're looking at two oxygen atoms, now far apart from each other. They aren't interacting. They're both treated as individual particles with their individual set of valence electrons. These two electrons, identical in every respect, have 2 electrons in this spherical 2s orbital. And for oxygen, it has 4 electrons in the dumbbell-shaped 2p orbital. The other oxygen atom has the exact same together. It has the exact same set of electrons. As we begin to push these 2 oxygen atoms together and see how they interact, we see that our spherical s orbital will begin to mix and interact with the other spherical s orbital of our other oxygen. The rules of electrons, of the wave nature of quantum mechanics, requires that we would preserve the number of places for electrons to live. So we start with 2 s orbitals. We start with 2 orbitals. As they move together and they begin to interact, to constructively and destructively interface, we still have to end up with 2 orbitals at the end of the day. Luckily, these sort of are nice equitable housing atomic cities that don't destroy the number of places that electrons live, just sort of changes what they look like. So as we push them 2 together and try to combine and interact these 2 3-dimensional waves, one way they're going to act and combine together is by adding together their wave natures, both positive phase or the same phase of the spherical s orbital. When these are pushed together, they're going to constructively interfere, and they're going to build up a wave, build up an electron density between the 2 centers of our oxygen atoms. And we're going to see previously we have sort of this electron cloud centered on each individual atom. Now it gets shifted to this region between the 2 atoms, creating a negative charge that will hold the positive nuclei together towards each other. This interaction, this sort of favorable positive adding of different atomic orbitals, is a stabilizing effect and generally makes the orbital that results from mixing these 2 lower in energy. We'll often call this, for this notation, a sigma orbital, a sigma molecular orbital that is formed from this interaction. Now, we have to preserve the number of electrons and the number of orbitals, so we created this one by pushing 2 together. We have to have one more orbital that's created by this interaction. And from a mathematical standpoint, also from sort of a wave intuition standpoint, in the same way that we can add these 2 orbital togethers, we can also subtract the orbital from each other. There's sort of the weird math of quantum mechanics that I won't require you to know too much about, other than the fact that the typical way that we interact these is that we add the orbitals and we subtract them to preserve 2 different new combinations. When I say subtracting an orbital, the best way to think of this is adding an orbital of a different phase, here positive versus negative, red versus blue, however you would like to think of it. Now we have 2 different waves approaching each other of different amplitudes, one positive, one negative, but still both the same shape, of course. As these are pushed together, we start to form that same type of destructive interference, which creates a node right in the middle of this pair of atoms. And again, this node indicates where there isn't electrons. This node, we can kind of think as being a big gap between our 2 atoms, between the 2 different positive and negative sides, sort of a canyon that gulfs between our 2 oxygen atoms, creating no electrons, no negative charge that could hold these 2 atoms towards each other. In fact, they're slightly repulsive in trying to push away from each other. For the same reason that this interaction of adding the 2 orbitals together is a stabilizing effect, subtracting these 2 orbitals is a destabilizing effect. And so, again, we sort of have a nice conservation of energy. For every time we add 2 orbitals together, we produce 2 new ones, same number of orbitals. One's going to be lower and one's going to be higher in energy. This one, sometimes we'll call a sigma orbital. A sigma star orbital. And this is really sort of the general way that we see the interaction of orbitals, interaction of these 3D waves. As we push them together, there's a stabilizing force, but also an equally destabilizing force. As we take our 2 s electrons, 2 each from each oxygen atom, we put 2 in the lowest one available to us, which we would call a sigma bonding orbital. because it creates a negative charge between our two positively charged nuclei that helps bond our two oxygen atoms together. We still have two more electrons left over that have to go in the next available orbital, which is a sigma star anti-bonding orbital. This is again a destabilizing force that tends to try to push these two atoms back apart, again because of the presence of this node. So if we only had two s orbitals on each oxygen atom, we would predict that as we push these oxygen atoms together, we would get a stabilizing force that pulls the atoms together, a bonding orbital. But we would also get an equally destabilizing force, an anti-bonding orbital. And so the net effect is that they wouldn't interact with each other. They wouldn't have anything to do with each other because any sort of positive interaction is balanced out by an equal negative destabilizing interaction. But of course, these are not the only electrons that would be interacted as we push these two atoms together. We also have our higher energy p orbitals. Looking at our p orbitals, we have the same set of rules. As we sort of push them together, we can add them, we can subtract them, and we'll get the same number of each orbital. But now we have different shapes, different symmetries. Rather than a spherical shape for our s orbital, we have these dumbbell shapes that point along our x, y, and z direction, and that creates differences in how those interact. We'll take our px orbitals, in this case for convention, the ones pointing in this horizontal direction, and we'll take a p orbital from our left oxygen and a p orbital from our right oxygen. And as we combine those together, we push those atoms together, the positive half of these orbitals can add up together in the middle, constructively interfering, producing a nice positive bonding type orbital between these two oxygen atoms. Electrons are going to be found predominantly, a large cluster of electrons found between our two oxygen atoms, holding them together, bonding them together, just like our lower sigma bonding orbital might be. We typically see a much stronger stabilizing effect as we push these p orbitals together compared to our s orbitals, just because they have really, really good overlap because of how sort of extended this p orbital shape is. So we create a very, very favorable bonding interaction by pushing our p orbitals together. But by balance, we also have to create this unfavorable anti-bonding by subtracting the two different ones from each other. We also have a set of p orbitals that point sort of parallel to each other here in the y direction, but also a set in the z direction coming out of the page. These ones still can add constructively, blue with blue, red with red, but because they're pointing sort of parallel to each other, there's not great overlap between these orbitals. So these are still far apart from each other. They still add together, but not as strongly, not as favorably, not as stabilizing as an effect. These p orbitals add together. They also can subtract from each other. And we see resulting stabilized orbitals, bonding orbitals, and destabilizing antibonding orbitals, but a much shallower change in that stabilizing effect because of this poor overlap between the two. We see that now that we've pushed these two atoms together, we have some bonding orbitals, sigma, sigma, and a pi type orbital, as well as the complementary antibonding sigma star, pi star, sigma star. In this case, we now have to consider the fact that for every set of bonding orbital and anti-bonding orbital, however much the bonding orbital is stabilized by, the antibonding is destabilized. But as we take inventory, we don't have the exact same number of favorable lower energy bonding orbitals and unfavorable anti-bonding orbitals. Overall, we have a net lower energy combination of these two oxygen atoms being pushed together than them being apart. If we were to take a quick inventory, the 6 electrons from this oxygen, the 6 electrons from this oxygen, 12 in total, will once again, like oxygen, like electrons do, fill from the lowest orbital on upwards, 2 each per orbital formed. And we see that we have 1, 2, 3, 4 pairs of electrons in a bonding, stabilized orbital that pulls these oxygen atoms together, versus one, two pairs of these destabilizing anti-bonding orbitals. So as a net effect, this pair of oxygen atoms gets more stability, lower energy by pushing their electrons together as opposed to being individually or separate as they were. It is not every bonding interaction is a net favorable one. Sometimes it gets canceled out. By inventory, looking at these combinations, we see that net effect is that there are two pairs, four bonding electrons, two sets of electrons that are holding and gluing these two oxygens together. We sort of think about this, and we'll call this the fact that we have two sets of net bonding orbitals, and that there is a double bond between these two oxygen atoms, one coming from a sigma type orbital, the other coming from a pi type orbital. We don't have to worry too much about the difference between that sigma and that pi, aside from knowing that both are stabilizing, both are lower in energy, favorable for electrons to move to, and creating a negative electron wave in between our two atoms that pulls our two positively charged nuclei together. Now, in this particular case, we see that because we have the same oxygen atom on both the left and the right of this diagram, that we would expect good symmetry in the shape of these bonding and anti-bonding orbitals formed. Because they're symmetrical, they have sort of the same atomic radii that we're pushing together, the same type and size and energy of orbitals, that we will see that the electron wave, this probability density where we find electrons, is evenly split between those two oxygen atoms. But of course, that is only true, or likely only true, when we have waves of the same amplitude and energy coming from the same atom. Of course, within our table of 118 elements, we probably rarely or less commonly have the same atom bonding with itself. We probably have different atoms of different elements who would still follow the same idea of forming these molecular orbitals from atomic orbitals. We have to now account for this idea that most elements are going to have different orbitals of different shapes, different sizes of different energies, giving us a very sort of different look at how their stabilizing sigma bonding orbitals might constructively interfere, or their anti-bonding orbitals might destructively interfere, still producing a node, but now creating sort of a shape that still remains quite similar to the original waves. If we share our electrons unequally, say between a carbon atom and an oxygen atom, once again building back to our periodic trends, oxygen has 8 protons pulling on these 2s and 2p orbitals, so all of oxygen's orbitals should be pulled lower in energy by this higher positive charge. We now see that there is a mismatch between the 2p orbitals and the 2s orbitals. They're still the same general shape, spheres versus dumbbells, but now this mismatch has some consequences. As we begin to move them together, our 2s orbitals now have a mismatch of shape, mismatch of energy, just like the waves in our simulation did. Because they're so mismatched in energy, we see that the resulting bonding orbital is still lower in energy. We still get some of that constructive interference, but it's not a lot of constructive interference because they're so mismatched. And in fact, our bonding orbital is very similar in energy, looks very similar to the original lower energy orbital. Still some bonding, still some stabilization, but not as dramatic as when we have perfect matching of our two orbital energies. We still have an anti-bonding orbital that is slightly destabilized, but not as much as when we had good energy matching. We have bonding and anti-bonding, but because it's energy mismatch from different atoms with different orbital energies, we don't see as strong of effect, strong of interaction between those two. Same thing is true when we have our p orbitals combined together. Again, this mismatch means that they are still stabilized and destabilized, but not as much as originally with better energy matching. Our p orbitals now pushed together now have a net set of bonding versus anti-bonding orbitals. These orbitals, mixed between the orbitals of carbon and oxygen, now are not quite so symmetric. We see that because our bonding sigma orbital from our 2s is effectively very similar in energy to our oxygen 2s, the shape of this orbital, where those electrons are found, where this wave is centered, is shifted very much towards the oxygen side, very much resembling just the original oxygen atomic orbital. Same thing for our anti-bonding sigma orbital. Very much looks like our original carbon 2s orbital. We still add them together. We still get constructive stabilizing interference, destructive destabilizing interference. But our orbitals, our mixed molecular orbitals, still look very similar to our atomic orbitals. There's certainly an uneven split of where these electrons might be found. In addition to our destabilizing and stabilizing forces coming from mixing our atomic orbitals, these orbitals are still waves. This 2s atomic orbital is a wave that interacts with the wave of this 2s atomic orbital and produces a sigma bonding orbital, which is itself, once again, just another wave, waves propagating on waves. For the same reason that our 2s orbitals can mix together to produce a new set of orbitals, our resulting molecular orbitals also can continue to interact with each other. You may think of this as if you were to get in a boat with your friend in the pond and you each create your own set of ripples. As you create your ripples, they sort of interact first, but those ripples interact with the ripples produced by those ripples, on and on and on until we have sort of a chain reaction of ripples reacting with ripples. What we notice about this interaction between the very mismatched carbon and oxygen orbitals is that this energy mismatching means there isn't really good mixing between those, not a lot of stabilizing and destabilizing force. Curiously, though, because of that poor stabilization and the particular energy levels, we see that this sigma star anti-bonding orbital is actually now very close in energy to this sigma bonding orbital. And any orbitals that are close in energy, regardless of where they come from, have the ability to mix and overlap. We also see that there is sort of a similar shape to them. While there is sort of different planes of symmetry, we see that both of them feature some of this blue positive amplitude between our two atoms, between our two nuclei. And so if we were to mix those together, just as we mix different atomic orbitals together, we could see some more constructive interference, some more destructive interference. We generally call this idea an sp mixing, reflecting that the idea that our two s orbitals can mix together, but effectively our s and p orbitals can also mix together if the energy is right and if sort of the shape is right. As these two sigma star and sigma orbitals, molecular orbitals, are mixed together, we get more positive constructive interference and negative destructive interference. Anytime we have positive constructive interference, we get lower stabilizing energy and higher destabilizing energy, resulting in new orbitals with different shapes. Now, we see sort of very different energy landscape, and we can now once again take stock of how many electrons are found in a stabilizing bonding orbital versus a destabilizing antibonding orbital. In this case, our stock and our count counts 1, 2, 3, 4 pairs in a bonding orbital that will hold this carbon and oxygen together, creating electrons that glue our two positively charged nuclei together, and only one anti-bonding orbital, this sigma star, resulting from this messy mix of sp orbitals from both carbon and oxygen. Overall, because we have a net 3 bonding orbitals compared to only one anti-bonding orbital, we can think of this as sort of a set of 6 electrons that are gluing these two carbon and oxygen atoms together, treating what we might call a triple bond, 3 sets of electrons. Now, we see in this particular example that we have sharing between the carbon and the oxygen atoms. These electrons are found in the middle, sort of between those two nuclei, again gluing the positively charged nuclei together. But compared to our oxygen-oxygen case, we see that they are shared unequally, that the shape of this electron wave, the shape of this electron probability density, isn't centered evenly between the two nuclei, but is shifted ever so slightly towards the oxygen. More electrons are found sort of on the oxygen side than on the carbon side. We generally recognize that the side that is lower in energy, in this case the oxygen, being more electronegative, stronger pull on these negatively charged electrons, will tend to sort of have the bulk share of the shared electrons. So again, between carbon and oxygen, we get sharing. We get a bond or 3 bonds between our carbon and oxygen, but it's not evenly split between our two atoms because of the lower, more stabilizing energy of this oxygen. Overall, most of our discussion and way that you can predict what happens between two atoms comes down to a very finite set of rules for how we can predict how these atomic orbitals will mix and overlap with each other. By and large, every time we produce mixed orbitals, we have to preserve the number of orbitals. And as we've seen, usually we combine them 2 at a time, giving us a stabilizing bonding orbital and a destabilizing antibonding orbital. Hopefully, we have a net number of stabilizing bonding orbitals that will hold our molecule together versus destabilizing antibonding orbitals, which will push them apart. The better overlap we have between the two and the closer the energies are, the more stabilization we'll see, the more destabilization we'll see. The difference between perfectly matched oxygen atoms with strong stabilization, strong destabilization, versus the mismatch between carbon and oxygen, giving a slight stabilization, slight destabilization, not as dramatic due to this poor matching of energy and overlap. Sometimes we may also mix atomic orbitals together, such as when we saw the S and P mixing, reflecting sort of the very messy, complicated nature of this molecular orbital theory of predicting how really 20, 30 something different waves will interact with each other now in 3 dimensions. To be perfectly clear, to leave maybe some anxiety, this molecular orbital theory is a more advanced way to discuss electrons and protons and how atoms interact. It's definitely a much more definitive one, but it is one that takes a moment to digest. And one that we talk very qualitatively so that you have an understanding of why we see some of the trends that we see. One other trend that we might see, and one that we saw in the last example, is that between carbon and oxygen, we had a very, very big mismatch in energy, really giving sort of an uneven splitting of electrons between the carbon and the oxygen. What happens if we have an extraordinarily large mismatch in their energy, such as between sodium and chlorine? Whereas carbon and oxygen on our periodic table are really only separated by one element. There's only a difference of 2 protons between carbon and oxygen, creating that slight difference in energies. If you compare something like sodium, found here on the far left of our 3rd period, versus chlorine, found on the far right of our 3rd period, there being a 6 electron 6 electron difference, 6 proton difference between those 2 elements, we expect to be a larger gap between the 3s and 3p orbital of sodium and 3s and 3p orbital of chlorine. These, even though they're terribly mismatched, still can mix together. We still get a sigma and sigma star bonding and antibonding, but because they are so mismatched, essentially our sigma bonding is just the chlorine 3s, and the antibonding is just the sodium 3s. Same thing for the p's. They are so mismatched that they do mix, they do form these molecular orbitals between those, but they are essentially just their original atomic orbitals between them because of this extensively large mismatch in energy. And if you were to look at the shapes, you would see that all of these bonding orbitals are essentially just the s orbital of our chlorine and the three XYZ p orbitals of our chlorine as well. Effectively, as we take the 7 plus 1 electrons, 8 total between sodium and chlorine, we fill from our bottom bonding on upwards, and we essentially only have 8 electrons to put in the 4 bonding orbitals here, which are predominantly just chlorine. Now, this technically does create a bond, a shared set of electrons between sodium and chlorine. There's a slight stabilizing effect, but as far as most chemists are concerned, the difference is so large that essentially is just transferring that singular Sol 3s electron over to the 3p orbital of chlorine. In these instances in which there is very little sharing and essentially an electron just transferred, we would more appropriately or more easily describe this as being a net transfer of our one electron, giving sodium plus having lost one electron and chlorine minus or chloride having gained one electron. And most of our chemistry can be described along this spectrum of how close the energy matching between our orbitals are and how evenly split or how unevenly split the resulting molecular orbitals look. At a very gross level, we describe this splitting and this sharing of electrons as bond polarity. How do we create a positive negative pole along these bonds? In cases in which the energy matching is exactly the same or very, very close, we generally see what we would call a non-polar or so-called pure covalent bond. And when you have a large, strong stabilizing effect between a bonding and an anti-bonding orbital, and we see the electron shares located very much evenly between our two atoms, giving us essentially a set of electrons that doesn't have a positive or negative phase, sort of evenly split between the two. We'll often draw that as a single straight line to represent that there is one pair of electrons, one bond holding A to B in this particular case. This is what we see with oxygen, and really anytime we have two atoms that are of the same type, same element, we'll see a pure or non-polar covalent bond. Many bonds, however, have a slight mismatch in energy, such as we saw between carbon and oxygen. In this case, because our electrons are not split quite so evenly, there is more electrons shifted onto this lower energy, more electronegative B side of this bond. We still have a covalent bond, electrons shared between our two nuclei, but not shared so evenly. This B side is going to be ever so slightly negatively charged, having more of those electrons. And by complement, the A side is going to be slightly positively charged. It's not one full electron's worth of charge. It's not one full plus or one full minus. And we often represent the idea that there is a slight positive and negative charge, a slight negative pole and a slight positive pole, by using the lowercase Greek delta, this little squiggly d thing, to show slightly negative, slightly positive side of this bond. In the far extreme, the third way that interactions might happen, the third way that atoms might bond, is that there's such a strong mismatch that we effectively treat it as a complete transference of electrons. In this case, one electron transferred from A to B to produce this pair of ions, cationic A, anionic B. Now, I present it this way because this really does exist along a spectrum. Each of our atoms are going to shift slightly, and the difference between the orbitals are going to vary in very, very finite, gradual, continuous degrees. And so categorizing, creating strong hard divisions between nonpolar, polar, and ionic bonds based on how those electrons are shared is very much sort of a bit of guesswork and very much a definition that chemists have sort of just said, we'll pick these numbers for now, we'll pick this sharing for now, but there's very much a margin between those, and of course they exist along a continuum or spectrum. But still, for a lot of our discussion, it's helpful to be able to break apart the ways interactions might happen by whether or not the electrons are shared equally in a nonpolar covalent bond, shared but unequally in a polar covalent bond, creating a slight positive, slight negative half of that bond of those shared electrons, or an ionic bond of completely transferred electrons from cation to anion. Now, a lot of our discussion of molecular orbitals will deal much more qualitatively with looking at how these orbitals mix and some surprising results from that. Very, very practically, we need some quick and easy rules to predict whether or not any pair of atoms found on our periodic table is going to form which type of these three bonds as their orbitals mix together. A very, very empirical, not always true, mostly correct way to do this is by using the Pauling electronegativity. Don't have to worry about who Linus Pauling was, chemist from maybe 60 years ago or so. But Pauling created a scale that ranks how electronegative each atom is, or each element is. A stronger electronegativity implies a lower orbital, more strongly pulling on each of those electrons. And so something like chlorine with an electronegativity of 3 has a lower set of atomic orbitals. A stronger pull tends to hold on to and tends to be the one that takes the electrons from something like sodium with a much more positive, or sorry, a much less positive electronegativity of 0.9. When we see large differences in their electronegativity by something that wants electrons versus something that doesn't want electrons quite as much, we typically see if there's a difference of at least 1.8 or so. Again, these divisions are kind of uh, uh, very generally made, and different chemists will have different definitions of where these divisions are. But if we see a large difference in their electronegativity, a large difference in their orbital energies, we'll typically see an ionic bond. So between chlorine's 3.0 versus sodium's 0.9, difference of 2.1 would allow us to predict that this should form an ionic bond. If we see something that is effectively about the same, difference of less than 0.4, such as between oxygen and oxygen has a difference of 0, of course, we would predict that they would share equally, forming this non-polar covalent bond. No difference in the electron density between either side of that bond. This middle region, somewhere between a difference of 0.4 to 1.8, is where we start to see this polar covalent bond. Again, it does exist in a range. There are some polar covalent bonds that are more ionic, some that are more nonpolar, but we generally try to break it down to these three categories just to make our lives a little easier. So you would see the difference between carbon and oxygen, 2.5 for carbon, 3.5 for oxygen, a difference of 1.0, would predict that we should have unequal sharing of those shared electrons between carbon and oxygen. Oxygen being a higher electronegativity, lower orbital energy means that oxygen should have more of that electron, should be slightly negatively charged versus carbon slightly positively charged. Different resources will have different numbers for electronegativities, different thresholds for these different ranges, but these are sort of general guidelines to get us started. And as far as this course is concerned, since you do have to answer questions and sort of we have to agree on things, we'll use these numbers to divide between those. And we'll use this table, which is also found in your textbook, as sort of the definitive set of how we calculate these differences in electronegativity to predict what type of bond we might have. The beauty of this is that it allows us to quite quickly go from a chemical formula and every pairwise set of atoms bonded together or interacting, and allows us to predict whether or not we have an ionic compound, which might have an empirical chemical formula, versus something that has polar covalent or non-polar covalent bonds, which would form a molecule, which would have a molecular formula, something like water H2O, for example. We'll explore this a little more throughout the remainder of our lecture, and of course, there's some room to practice in our problem set. But to everyone's delight and relief, we mostly try to deal with these sort of results of molecular orbital theory. It's a lot faster, is generally true. There are some exceptions to it. Well, there's several exceptions to it, but it allows us to do a lot more quick and tractable work by taking these approximations, these estimated ranges, to go from a chemical formula to a prediction of their bonds and their properties. Uh, it is helpful to know how we might be more thorough using these MO theory diagrams, molecular orbitals, combining them together to see their bonding patterns, largely because there are some advantages. Some things are explained more appropriately by one theory versus these approximations. One type of bond which does exist, really the fourth category of bond, which we will not discuss too much in detail in this class, as it's sort of a topic of more advanced chemistry and some material science, is a metallic bond. This is what you might find holding two atoms of aluminum together or two atoms of iron together. This metallic bond still stems from combining different atomic orbitals, creating a split between a bonding and an anti-bonding orbital. But because our piece of metal, our chunk of iron, consists of billions upon billions of atoms, each with billions upon billions of orbitals, we not just get two orbitals combined together, we get a billion orbitals combining with a billion other orbitals. The result of which is that every time we combine them, we still get stabilizing interactions and destabilizing interactions. And we end up creating sort of a near infinite set of orbitals that are all spaced very, very closely to each other. Because these orbitals are spaced very, very closely to each other and mixed very, very intimately, essentially there isn't a billion individual bonding orbitals. There's sort of a sea of orbitals all spread evenly throughout this piece of metal. The fact that there's so many orbitals overlapping in space, spaced very closely to each other, is what gives metals their conductivity, the reason why electrons can move quickly from one end of a copper cable to the other, because their orbitals are spaced so closely together, allowing them to hop quite easily from one to the other. A lot more details about how that works as you advance through your studies, but just so you're aware that there is a fourth type of bond that's different than a covalent bond, different than ionic bond, we would call a metallic bond. Now, the reason why we sort of use MO theory, why it exists, and where it comes in, is that it allows us to make a lot of predictions that a lot of other theories sort of have had to piece together very unique rules with lots of exceptions, a lot of caveats. It doesn't help us predict as accurately as MO theory. MO theory, molecular orbital theory, really is a definitive way that chemists, biologists, material scientists figure out how matter behaves. We often do it computationally because these are very complicated, extensive interactions, but we can still take the results and use that to build some intuition. One thing we can use MO theory for, molecular orbital theory, is to predict the shape of molecules based on how these orbitals might overlap. We know H2O, the chemical formula for water, implies that there's two hydrogen and one oxygen. And we'd probably predict, for reasons of symmetry, that we would have two hydrogens on either side of an oxygen. But there is a question, and it's not obvious without knowing a little more, whether or not we would predict to have a completely linear arrangement of HOH at a bond angle of 180 degrees, or some sort of different arrangement, different shape. And we could envision we might have a 90-degree bond angle between this HOH. How do I know, without looking at a single molecule of water, what the angle, what the shape of this particular molecule might be? One reason why we might care about it is that this HO bond, hydrogen-oxygen, is a polar covalent bond in which the hydrogen is slightly positively charged and the oxygen is slightly negatively charged, as of course is this hydrogen as well. In this linear shape, we will see that there is a pair of dipoles, pairs of positive and negative charges that sort of cancel each other out and mirror each other out. Because there's sort of symmetry to this linear molecule, there isn't a positive half and a negative half of this molecule. It is overall sort of a neutral, non-polar molecule. That's different if we have a bond angle between our hydrogen and our oxygen, in which now these differences in positive and negative charges add up to each other. They all begin to point in the same direction, reinforcing each other, giving us a molecule that overall has a slightly positively charged end and a slightly negatively charged end. So without doing a lot of experiments, potentially there's a new molecule. How can I predict which shape these will adopt and ultimately predict something about their properties? With MO theory, we can begin to examine how the shape of their atomic orbitals might overlap to create stabilizing bonding and destabilizing antibonding orbitals. And we see that here for water, between hydrogen, oxygen, and hydrogen, going from a linear 180-degree bond angle to this bent structure at 90 degrees, we have some orbitals that will become more favorable, more stabilizing, as we better align positive with negative. Now having positive aligned with positive as you offset these. And of course, some will become destabilizing as you break the overlap, as you shift the arrangement of these atoms. MO theory, from a computational as well as a conceptual level, we'll take here the result given in this Walsh diagram, shows that as we go from a linear water structure to a bent water structure, we have some orbitals that are favorably stabilized, some orbitals that are unfavorably destabilized between the two. We will predict from this analysis, from MO theory, that the true structure, the true answer for what shape is a water molecule lies somewhere between these two extremes, where we have some stabilization to balance out the destabilization, but before it gets inverted, we might rest at some sort of bond angle between 180 degrees and 90 degrees. In this case, computationally, you would find that the sweet spot, just around here, where we have a net stabilizing effect, is about 105 degrees, which matches what we see experimentally with the angle of a water molecule. So I point this out because we can do a lot of powerful things with MO theory, but it is very tricky to do in practice, particularly with pen and paper. And most chemists, including myself, will do this computationally with a lot of different software pieces that tries to do a lot of this very complicated matching of 3D shapes and judging overlap and things like that. And so where we go from here recognizes that MO theory is the way that the world works. It's important you know the most fundamental real rule that we have available to us. But to do things with that rule, to make it a little more tractable, we're going to simplify the results of MO theory and try to have some takeaway simplified rules that allow us to do a lot more with a limited number of cases, because it's not always true, not always predictive, but good for about 80% of the chemistry that you will do. These simplified rules you may have done sort of at high school levels of chemistry or before. We will call Lewis structures and valence shell electron pair repulsion theory that we will come back to after we take a little break. So we will take a break, give everyone a chance to rest and stretch their legs, find some coffee, some food, some water, whatever it is, and we will come back at 11:15. According to that clock. If you have questions on the problem sets or on the lab report, things like that, this is also a good time to tackle that. Otherwise, you're always welcome to find a dark, quiet moment to yourself and just steel yourself for the second half of this lecture. 11:15.